I'm Christopher Tricola, and I'm going to be one of your instructors here for your Solar Power Pro certification. First thing we're going to be learning about is electricity and solar. So let's get to it. Now, we need to learn a bunch of stuff about electricity today to make sure that we have a good understanding and grasp on how solar is going to be affecting the usage inside the customer's home. Because when you get your home energy bill, it lists the usage in kilowatt hours. But when you go to the store, you see things like 12-watt light bulb, 9-volt batteries, and vacuum cleaners with 15 amps of sucking power. What do these numbers mean? And why are they different for each type of product? Well, it's the role that each part of the circuit is going to play in making that function. So electricity runs inside of a circuit. And it's important because several things have to happen in order to be able to make an electrical circuit for electricity to flow in order for the work to be done. So you can think of a circuit kind of like a faucet in your kitchen sink if you want the water to come out. So you need a couple things to happen. First, you're going to need the water itself, and then you need some pressure to force it through the pipes and out of your faucet. An electrical circuit uses electrons to carry the electricity, kind of like the water in your faucet. But those electrons need something to push them along the circuit. Now, voltage is important. It's a force associated with the electrical current that is measured in units known as volts. Power companies use high voltage. We've seen these signs before. They're all over the place to let you know that you can be electrocuted, right? Power companies use high voltage to move electric power over long distances. This electrical pressure is what we call voltage and is often provided by two terminals, one with a positive charge and one with a negative charge. Now, we've all seen that before, just like this picture here in the back, a battery, a positive and it has a negative. So let's talk about this a little bit. Voltage equals pressure. This might be on the test. Voltage equals pressure. So when we hear voltage, we need to associate that with the pressure that's being provided to be able to move the electricity across the distance. Electrons flow from the negative and through whatever you're trying to power, and then into the positive end where they'll stay unless your battery is rechargeable. If it's rechargeable, it's going to move back to the negative so you can reuse all those electrons again. So if you're plugging something into the wall, this voltage is instead provided by the power company. So although voltage just measures how strongly electricity is being pushed through the circuit, it's important because many circuits are designed only to accept a certain number of volts. Next thing we need to learn about are the amps. Now, what is an amp? A lot of people think of an amplifier. That's not what it is. In electrical terms, amp is short for ampere, which is a unit of how much electrical charge is flowing past a given point in 1 second. So, when you put volts and amps together, you can tell how much current is flowing and how hard it's flowing. So here's the power formula. Amp equals flow. So when we're talking about voltage, we're talking about the pressure. When we're talking about amps, we're talking about the flow. So our power formula is pretty simple. It's P equals I times V. Well, what do those mean? Well, P is going to be the watts. In this power formula, we're trying to determine the wattage that's being delivered, which means we have to multiply the amps times the volts. So when you put volts and amps together, you can tell how much current is flowing and how fast it's flowing. So let's suppose you hooked up a water wheel to a generator and you needed to create some power. If we use a water pistol to push that through, it's going to have a really small nozzle, which means that the total volume flowing per second, there's not a lot of it, but there's a lot of high pressure, and that high pressure is going to be enough to turn that wheel at a certain speed. So that's what we're going to measure here with the water gun, is how much pressure is being pushed out to be able to determine the speed of that water wheel. Now let's use a water hose instead. It has a much wider nozzle at the end, right? More water's flowing per second, and it ends up spinning the wheel at the same speed. So why am I explaining this to you? Well, let's put this back in electrical terms. So if we think of the hose and the water gun as pushing out electricity instead of pushing out the water, you could say that they're delivering the same number of watts because it ends up spinning the wheel at the same speed. So let's try an example for electricity. Let's get our power formula put together. And let's say you have a computer with an 1100 watt power supply at full load in North America with a 110 volt outlet. We need to figure it out at full power how it's going to operate. So we're going to figure out the amps because right now we have the wattage and we have the volts. So we reverse our power formula and we're going to divide our wattage by our voltage, which is going to give us 10 amps. Now, let's say we take that same computer, we need the same watt supply, but we're going to use a 220 volt outlet instead. Well, it's going to change slightly. So now we're going to divide 1100 watts by 220 volts, which is going to give us 5 amps. Will the computer work? That's what we're trying to figure out here. In this case, the answer is yes. Because the wattage is the same, the computer will work the same in both places, even though the volts and the amps are different. Because we need an 1100 watt supply in order to be able to power that computer. Now, let's go over these basic definitions one more time before we move forward. Voltage is like the pressure that pushes the water through the hose, right? So when we think of voltage, we need to think of pressure. It's measured in volts, and you'll usually see that with a V. Current, it's like the diameter of the hose. The wider it is, the more water will flow through it. This is measured in amps. We'll usually see an I, or we'll see the A. Resistance we're going to learn a little bit more about later, but we're going to give you that definition now so that you can recognize it. Resistance is like the sand in the hose that slows down the water flow, or even kinking a hose. It's going to slow the water flow. It's measured in ohms. We usually see the ohm symbol or an R in our power formulas when we're determining these. Now, we understand the basic definitions of voltage, amps, and resistance. So what about kilowatt hours? So as we talked about in the very beginning, your bill is rated in kilowatt hours, and it's how you're charged by your utility company. So what are kilowatt hours? Is it a unit of time? It has the word hours in it. No, scientists absolutely hate us and they want to confuse us. It's not a unit of time. It's actually a unit of energy. Watts and kilowatts express how much energy is consumed per chunk of time. This is called power. It's not the same as energy, and kilowatt hours are a unit of energy. So, utility companies will charge you in kilowatt hours. Now, kilowatt hours is normally expressed in kWh, and kilowatts is expressed in kW. And they are completely different things. The customer system size is in kilowatts, and that's based on the number of kilowatt hours the customer needs the system to produce. Now, I said watts and kilowatts, right? And that's going to be the power, which isn't the same as energy. So let's talk about that for a quick second before we get on to any formulas. So watts are not the same as kilowatts. You get the number of kilowatts when you divide the number of watts by 1,000, or multiply the number of kilowatts by 1,000 to get the number of watts. So if you have an 8,000 watts and you want to figure out the kilowatts, divide it by 1,000, you'll have 8 kilowatts. If you have 9.7 kilowatts, you multiply that by 1,000 to get 9,700 watts. So kilowatts is the size of the system. Kilowatt hours is going to be the energy that it produces. Let's dive into that. A kilowatt is a measurement of power, while a kilowatt hour is the length of time something can use a kilowatt. 1 kilowatt hour is equal to 1,000 watts sustained for 1 hour. PV solar system sizes are calculated in kilowatts. The size of the system is determined by how many kilowatt hours is needed to be produced. Let's have a quick solar rundown. This is what we call a solar-only system. There's no storage capability whatsoever, and there's no battery backup built into the system. Because of that, any excess power is going to be generated, sold back to the grid. So let's talk about this for a second. We know that we need to find out the homeowner's kilowatt hour needs for the home. Then we can build the system size. Once that's done, the PV system generates power from the panels. The grid needs alternating current and the house needs alternating current. The panels produce direct current or DC. That's converted at the inverter, which is usually installed behind the panel or on the side of the home. So once it's converted from direct current to alternating current at the inverter, the house will be powered with this energy. Excess power is then sold back to the grid in the form of bill credit. Because this is a solar-only system, when the grid is down, the system stops working. We're going to learn more about that during the inverter section. But for right now, the things that you need to take out of this are excess power generated is sold back to the grid. The inverter converts from direct current to alternating current. And when the grid is down, the solar system stops working.